today's do now, it's 2 multiple choice questions. So the do nows will be practice multiple choice or free response questions based on what we've been talking about. So both of these questions came from either Unit 1 or Unit 2. With these, since they are multiple choice, we will do them without a calculator. So for number 1, a sample of a compound that contains only the elements C, H, and N is completely burned in oxygen to produce 44 grams of CO2, 45 grams of H2O, and some NO2. A possible empirical formula is, and it gives us 4 options. So we know that it's an empirical formula question. So if you remember the steps for empirical formula, take your percent to grams, if it starts with percent, then grams to moles, divide by the smallest, and then if needed, multiply until whole. This last multiplication part is only if when you divide by the smallest number of moles, you end up with a decimal like 0.25 or 0.5. So we know that these are our steps for empirical formula. If we take a look at this question again, we don't have percents to start, so we're already given grams. Now, if we think about what they give us, this is a unique type of empirical formula question. This is a combustion analysis question. We looked at combustion analysis at the very beginning of the year, but all it is just a specific type of empirical formula question. Remember, when we go grams to moles, we are going to moles of individual atoms. So what we're going to do is we're going to start with our given information. We have 44 grams of CO2, and we have 45 grams of H2O. The goal is to get to moles of individual atoms from the empirical formula. So we know that we need atoms of C, atoms of H, and atoms of N. Now, because it just says some NO2, they don't give us an actual amount. What we're actually going to do is we're just going to focus on C and H. And based on C and H, we'll be able to figure out our answer. So we don't have to worry about percent to grams because it was already given in grams. So now we're going to go grams to moles. So I'm going to go from grams of CO2 to moles of CO2. When you have to look at molar masses, round the molar masses from the periodic table. Carbon is 12.01, just use 12. So carbon is 12. Each oxygen is 16. 16 times 2 is 32. 12 plus 32 is 44. So we went from grams to moles of CO2. Now to find an empirical formula, it is individual atoms. So what you need to do is you need to figure out for every 1 mole of CO2, how many carbons are there? 1, right? In 1 mole of CO2, there's 1 carbon. Now look at this math. 44 times 1 times 1. So you have 44 on the top. You have 44 on the bottom. 44 divided by 44, right, is 1. Now we look at the same thing for water. We're going to do the exact same thing. Go to grams to moles, and then from moles of H2O to moles of H. So look up the molar mass of water. Well, calculate the molar mass of water. Okay, so if we take a look at this, I'm going to show you how we can actually do this math without a calculator. Now, here's the part that most people will miss with this empirical formula question. For every 1 H2O, how many H's are there? There's 2. This ratio is what people will miss with combustion analysis. Now, here's how you can go through and how you can solve this without a calculator. You don't have to necessarily multiply everything across and divide by what's on the bottom. Reduce where you can. So I'm going to try to simplify 2 and 18 because I know that 2 goes into 18. How many times does 2 go into 18? 9. So now instead of 2 over 18, I'm going to do 1 over 9. So now you have 45 times 1 times 1 on the top, and you have 9 on the bottom. What's 45 divided by 9? 5. So now we went grams to moles. Now in this case, we can see the ratio right away because the numbers worked out, but you would divide by the smallest. The smallest here is 1. So we have a 1 and a 5. So we need to look for the answer choice that has 1 carbon and 5 hydrogens. There's only one option that has a ratio 1 carbon to 5 hydrogens, and that's B. So it's okay that it says some NO2. That's okay. Just look at the ratio of the other atoms. Now for number 2, this is to gravimetrically analyze the silver content of a piece of jewelry made from an alloy of silver and copper. A student dissolves a pre-weighed sample in nitric acid. Ag plus and Cu2 plus ions form in the solution. Which of the following should be the next step in the process? So gravimetric analysis we talked about yesterday. Gravimetric analysis deals with precipitation. I don't mean rain, I mean the formation of a solid. Right? Precipitation is the formation of a solid in a chemical reaction. So knowing that it specifically says that we are gravimetrically analyzing silver, that means that our goal is to actually get solid silver out of this mixture. So all you have to do is you need to read the answer choices to figure out which one of those answer choices talks about getting a solid out of the mixture. So if we read through each of these, the only one that talks about forming a solid is D. When we add a solution that contains an anion that will form an insoluble salt, that means it's forming a solid with one of the metal ions. Then after that, we would be able to filter, we would be able to collect the solid, and then we could determine how much silver we had. So number 1 was looking at math without a calculator. We'll continue to look at those types of questions. Number 2 was focusing specifically on gravimetric analysis, which is the idea that we mix a solution to precipitate a solid, and then we would filter it, collect it, find its mass. Any questions on the do now? So again, this unit, unit 3, covers intermolecular forces. It covers gases. It covers solids, and it covers solutions. Just to kind of put into perspective what Unit 3 all covered, it took us about 2 months to cover everything that was in Unit 3. And so that's why this does make up anywhere from 18 to 22% of the AP exam. We see these questions a lot more in multiple choice. Not that we won't see any in the free response, but we tend to see a lot more of these types of questions within the multiple choice. So a general overview of this unit. There are 13 topics. We start with IMFs, we transition into solids, and then into gases, then solutions, and then finally we focus a little bit on spectroscopy and looking at waves and Beer's Law, which we did as a lab right before Christmas break, I believe. So just a quick review, because we're going to talk about intermolecular forces. You'll notice this is not a topic in this unit, but this goes back and reviews some stuff from Unit 2. So a quick review, polarity of molecules. When we're looking at intermolecular forces, we have to make sure that we can identify polar versus nonpolar molecules. So remember that a nonpolar molecule, all of the bond dipoles will cancel out. So the carbon-oxygen bond itself is actually polar. But when you put 2 carbon-oxygen bonds directly across from each other. You think about polarity as a tug of war. Well, both of the oxygens are pulling evenly. That actually cancels both of these polar bonds out, and that creates a nonpolar molecule. Something else to remember with nonpolar molecules is if we have something with all C's and H's, that's going to create a nonpolar molecule. So if we have something with all carbon-hydrogen bonds, that's going to be nonpolar. A polar molecule, the bond dipoles will not cancel out. So in the case of water, you have oxygen as the more electronegative atom. The oxygen is actually pulling the electrons toward it from both the first hydrogen bond, covalent bond, and the second hydrogen covalent bond. So since oxygen is pulling the electrons toward it from both directions, we're going to have a partial negative side up here. That will leave the hydrogens as partially positive. That creates a polar molecule. So it's important that we can distinguish nonpolar from polar molecules. Remember the fundamental shapes: linear, trigonoplanar, tetrahedral, trigonal bipyramidal, and octahedral. Assuming that all of the terminal atoms, all of the outside atoms are the same, those will all be nonpolar. Typically, if we see lone pairs on the central atom, that will make a polar molecule. So just a quick review of polarity of molecules. So this puts all of the intermolecular forces information onto one slide. 3.1 in the unit guide covers intermolecular forces. And so in 3.1, it actually lists all of the intermolecular forces, talks about polarizability for dispersion, but I'm going to talk just briefly about each of these intermolecular forces. So first, we have London dispersion forces. Remember, dispersion forces exist between all molecules. So dispersion forces exist between all molecules. Dispersion forces are caused by the electron cloud being distorted. So the charge in an electron cloud is being moved to one side or another. It creates this partial positive and partial negative side, but it's temporary. The key word, the big key word with London dispersion forces is polarizability. Remember, the more polarizable the electron cloud, the stronger the dispersion force is. We can tell when an electron cloud is more polarizable by the more electrons the substance has. So if we're comparing properties of all of the halogens, F2, Cl2, Br2, and I2, all four of those are nonpolar. They have electronegativity differences of 0. Iodine, I2, has the strongest dispersion forces because I2 has the largest number of electrons. We're talking about total electrons, not valence electrons. And so I2 has the most number of electrons. It's going to have the most polarizable electron cloud out of these four and the strongest dispersion forces. Now on this slide, I also tied in the properties. So remember, the stronger the dispersion forces, the higher the boiling point, because it takes more energy to overcome those intermolecular forces. Here's the most important thing. Do not explain the strength of dispersion forces based on mass. You have to explain dispersion forces based on the number of electrons, the polarizability. After dispersion forces, we see dipole-induced dipole. Now, we don't see these as often, but dipole-induced dipole. So induced dipole means it's a temporary partial positive and partial negative side. This is formed between a polar molecule and a nonpolar molecule. Example, HCl and Cl2. So we bring a polar molecule close to a nonpolar molecule and we get a temporary attraction. It's very temporary. Then we go to dipole-dipole, present between two polar molecules. So that is when the partial negative side of one molecule is attracted to the partial positive side of another. An example, if we want to look at HCl, because Cl is more electronegative, Cl is going to carry the partial negative side. And then hydrogen carries the partial positive side. Notice this is between two molecules. Intermolecular forces are between two molecules. So the attraction between this Cl and this H of another molecule, that is a dipole-dipole force. The strength of dipole-dipole forces is based on how polar the molecule is. So the more polar the molecule, the stronger the dipole-dipole forces. Then we move down to ion-dipole forces. We'll look at these more when we talk about solutions, but ion-dipole, we have an ion and a polar molecule. So an example is Na+ in water. When you have an ion attracted to a polar molecule like water, that force of attraction is an ion-dipole force. The higher the charge of the ion, the stronger the ion-dipole forces. When we're looking at strength of attraction, we can think about Coulomb's law. So as we increase the charge, we increase the strength of attraction. As we decrease the distance, so if we make it smaller, that also increases the strength of attraction. And then finally, we get down to hydrogen bonds. So hydrogen bonds are a unique type of dipole-dipole force. We have hydrogen covalently bonded to NO or F, and then that hydrogen is attracted to NO or F in another molecule. When we think about dispersion, dipole-dipole, hydrogen bonds, so all of these intermolecular forces, remember the weaker the intermolecular forces, the lower the boiling point, and the higher the vapor pressure. So for those that need a quick refresher on vapor pressure is the pressure of the gas above a liquid. So the question that we think about with vapor pressure is how easy is it for the liquid, all right, so let's say we have an Erlenmeyer flask, and we have a liquid in here. How easy is it for all of these liquid molecules to escape and become a gas? Well, that's based on the strength of intermolecular forces. If these have weak IMFs, so if it's easy for this liquid to become a gas, well, then we would expect a lot of the liquid to escape and become a gas. Well, the more gas we have up here, the higher the pressure, which is why the weaker the intermolecular forces, the higher the vapor pressure. If we look at the other way, the stronger the intermolecular forces, the higher the boiling point, and the lower the vapor pressure. So when you're looking at any kind of data, we see a lot of multiple choice questions having us look at boiling point. As soon as you see boiling point, write down IMFs and look at the intermolecular forces. Remember that there are times when dispersion forces play a stronger role than dipole-dipole forces. Hydrogen bonding is typically going to be the strongest, and that's going to play a role the most, but dipole-dipole and dispersion can depend. So always use the data that they give you to answer questions on intermolecular forces. So just to look at hydrogen bonding really quick, kind of looking at the diagram itself. So on the right-hand side of the slide, we actually see DNA. We've seen some multiple choice questions where you have to identify intermolecular forces. You have to identify hydrogen bonds. Notice how you have a hydrogen covalently bonded to NO or F, and that hydrogen just needs to be attracted to NO or F of another molecule. Here, hydrogen covalently bonded to N, and then that hydrogen is attracted to an O in another molecule. Same thing here. Hydrogen covalently bonded to N, covalently bonded to N, covalently bonded to N. If we had a hydrogen covalently bonded to a C, that would not hydrogen bond. The hydrogen has to be bonded to N, O, or F in order for it to have the potential to hydrogen bond. H will be in the middle, and then N, O, or F has to be on both sides. So hydrogen bonding is why water has such unique properties, because it's a very strong intermolecular force. Now remember, it's still an intermolecular force, so it's still between molecules, but hydrogen bonding is the strongest of those intermolecular forces. So then we move on to topic 2. And topic 2 actually looks at properties of solids. So topic 2 focuses on ionic, covalent network, molecular solids. So we've looked at all of these. This was chapter 12. So IMFs was chapter 11 for us. Solids was chapter 12. And we talked a little about ionic solids yesterday. Yesterday we talked about how we have to have cations and anions alternating in the structure of an ionic solid. We said cations are smaller than anions. But now some properties of ionic compounds. So ionic compounds are brittle. That means they break easily. So for example, I have this block of sodium chloride. And I have this block of NaCl. If I drop this block of NaCl on the ground, it's going to shatter. It's going to break. That's because ionic compounds are brittle. When this hits the floor, it actually moves some of the ions in the crystal. And when it moves the ions, notice how now we have positives next to positives and negatives next to negatives. Well, like charges repel. So when the crystal lattice gets moved and the ions get shifted, they're going to repel, and that causes this substance, this ionic solid, to break. So that's why ionic substances are brittle. Now, one of the most important properties of ionic compounds is what I have down here. We've seen lots of multiple choice questions that uses this information of ionic substances. Ionic compounds do not conduct as solids. So if I try to test the conductivity of this block of NaCl, I have that conductivity meter that I have the light bulb. If I stick the prongs onto this NaCl, it's not going to conduct. However, if I put this block of NaCl into water and I dissolve it, or I melt it, it will conduct electricity. When ions are able to move, when ions are mobile, the substance will conduct. So ionic compounds do not conduct as solids, but do conduct as liquids or aqueous solutions. So if you are trying to test if something is ionic, the first thing that you should test is conductivity as a solid, and then conductivity as a solution. This is the only type of solid that has this unique conductivity properties. Everything else either conducts or it doesn't. So we also have covalent network solids. So covalent network solids are only carbon or silicon, C or Si. And covalent network solids are on the back page of topic 2. So with covalent network solids, only carbon or Si. We have 2 examples here, graphite and diamond. These are both elemental carbon. The difference between graphite and diamond is how the substance is bonded covalently. A covalent network solid is so unique because the network is of covalent bonds. And so with graphite, you have these layers that are covalently bonded together. Diamond is more of this 3-dimensional structure. And due to this 3-dimensional structure, it makes diamond a very hard substance. It's very hard to break. And so both of these are carbon, both of these are covalent network solids. Now with covalent network solids, especially diamond has very high melting point. So we expect high melting points for covalent network solids. And that's due to, again, the covalent bonding between all of the atoms in the solid structure. Then we look at molecular solids. So covalent network solids are just C or Si, that's it. If it's any other non-metal, we're looking at molecular solids, and molecular solids are held together with intermolecular forces. So water, ice is water molecules in the solid phase. Ice is held together with hydrogen bonds. It's an intermolecular force. Iodine, I2, is nonpolar. There's no electronegativity difference. And so I2, because it's nonpolar, the solid is held together with dispersion forces. So with molecular solids, because they're held together only with weak intermolecular forces, they tend to have low melting or low boiling points, because intermolecular forces are much weaker compared to covalent bonds or ionic bonds. And so then what we have on this slide are properties of solids. And essentially this table is taking what is on the 3.2 topic page and kind of just putting it into a table for us to look at. So it has ionic, molecular, covalent network, and metallic. And we talked about metallic yesterday, so I wasn't going to put it on here again. But notice for melting and boiling points, molecular has low melting and boiling points. Everything else has high melting and boiling points. So if it says, you know, this substance has a low melting point, more than likely then it's a molecular solid. Conductivity. Again, conductivity is useful because if the solid conducts electricity, that means it's a metallic solid. So if the solid conducts, it's going to be metallic. However, if the solid doesn't conduct, but the liquid or aqueous solution does, then it's ionic. So this shows different properties of each of the types of solids. This essentially takes chapter 12, so solids was chapter 12 for us. This takes everything we did in chapter 12 and just puts it into a table for us to be able to reference all of these different properties. We've seen properties of solids as multiple choice questions, and we've seen it as some of the explanation part of free response. So we've seen both types of questions. This is another slide that shows ionic versus covalent and looks at the bonding, but this is essentially just pulling out ionic and covalent from the other slide. Now the last part of 3.2 is essentially just saying that if we have very large molecules, or we have biological molecules, very long chains of different atoms, elements, metals, nonmetals, in a large molecule, we could potentially see multiple types of intermolecular forces all in one long molecule. It's very common to see. So for example, we could see an ionic bond. We could see a hydrogen bond. We could see London dispersion forces all in the same molecule. So that's okay if we have this big long molecule and we have different types. It's not just one intermolecular force exists in one molecule. Remember, everything contains dispersion. We might also see dipole-dipole. We might also see hydrogen bonding. So then topic 3 transitions from solids, and then we start to get into individual states of matter. So with a solid, look at our particle diagrams. Solid, the molecules are close together. They just vibrate in place. With solids, we have 2 different types. So we can have a crystalline solid or an amorphous solid. Crystalline means it has a regular pattern. Amorphous means that there's no regular pattern. It's just atoms there. Right? So crystalline has a regular pattern, amorphous does not. Then we get to liquids. So the molecules are still pretty close together, but they're more random. And then gases, the molecules are very far apart. Now, if we compare it to intermolecular forces, all the way at the bottom of this slide, solids have stronger intermolecular forces than gases. So if you're comparing intermolecular forces, if one substance is a solid and one substance is a gas at room temperature, they're essentially telling you the strength of the intermolecular forces. The solid is going to have stronger intermolecular forces because the molecules are held more closely together. In a gas, that's going to have very weak intermolecular forces because your particles are far apart. So solids will have stronger IMFs than liquids, and then gases will have the weakest. Now we get into gases. So topics 4, 5, and 6 look at gases. We are not going to hit every single detail of gases. So gases was our unit 3. So if you know that gases is something that you have to go back and review, gases was unit 3 for us. Within gases, here are the 3 equations that are on the equation sheet. If we want to calculate pressure, volume, number of moles, or temperature, we can use the ideal gas law. Remember, on your equation sheet, you have the values of R. You have all of the values of R given to you on your equation sheet. Something to keep in mind, temperature has to be in Kelvin. When we deal with gases, you are using the absolute temperature scale, which means you have to use Kelvin. Look at your value of R and look at your units of R. That tells you what units you need for everything else. Now, an equation that will be useful that is not on the equation sheet is the combined gas law. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. The combined gas law takes all of the gas relationships that we'll look at on the next slide, and it puts them into one mathematical formula. When you plug things in, units need to be the same. Temperature has to be in Kelvin. If we have a mixture of gases, the pressure is independent. So the pressure of gas A doesn't matter what the pressure of gas B is, doesn't matter what the pressure of gas C is. But if we want to find the total pressure, we can add them all up. If we put 3 different gases into one container, assuming that we're not changing the volume, if we put 3 gases into the same container, we just add the pressures up. Now, if you change the volume, that becomes a combined gas law question. You can also calculate the partial pressure using total pressure and mole fraction. So mole fraction is part over whole when you're dealing with moles. You can also calculate mole fraction using your pressures. So these 3 equations are on the equation sheet. The combined gas law is not, but you need to know the combined gas law. When you're changing conditions, so you go from an initial set of conditions to a final set of conditions, that's the combined gas law. So looking at the variables. So this is just a quick review of the variables of gases. So when it comes to looking at pressure and temperature, it's important that we know how they're related. So if we think about pressure and temperature, I'm just going to draw a graph over here, P versus T. So if I have absolute zero, there's no movement. If there's no movement, is there going to be any pressure? No. Pressure is based on collisions. Well, then as we increase temperature, we start to increase the speed of the molecules. As we increase the temperature and they move faster, what's going to happen to collisions? They're going to increase. So P and T is a direct relationship. Now, if we look over here at pressure and volume, in a very, very small container, right, a very small container, what's going to happen to the number of collisions? They're going to increase. All right, a very, very small container, collisions are going to increase. As we increase the size of the container, collisions are going to decrease. Pressure and volume is the only one that is inverse. I would make yourself a note somewhere that pressure and volume are the only two variables that are inversely related. Everything else is direct. So that means that V and T is directly related. So every other set of variables will be a straight line except for pressure and volume. You don't have to worry about the individual gas law names. You don't need to know Boyle's law, Charles' law. You don't need to know that. You just need to know how they're related. Remember, pressure is based on collisions. Before we move on to 3.5, I want to just review one major demo that we looked at with gases, and that's this diffusion demo that's down here at the bottom. So we still need to be able to talk about diffusion and effusion of gases. And we did this demo in class. I showed the animation on the board. Diffusion is based on the movement of gases. The lighter the gas, the faster it moves. The heavier the gas, the slower it moves. That's the idea of diffusion. So when you're looking at how fast the gas will move, the speed of the gas, look at its molar mass. NH3 actually moves faster in the container than HCl because NH3 is a lighter gas. That's why they actually meet closer to HCl rather than in the middle or closer to NH3. Speed is based on molar mass. So then we will look at 3.5. 3.5 looks at the kinetic molecular theory. Now, I'm not going to read through the kinetic molecular theory itself. You can look at that, those postulates for the kinetic molecular theory. This is the most important thing that I want to focus on right now. If the temperature is not changed, no matter what else the question tells you, the average kinetic energy of a gas will not change. Average kinetic energy is the energy of motion. Takes into account mass and velocity. Average kinetic energy is measured by temperature. Please do not miss the multiple choice questions that give you all of this information and says, the question will say, if temperature is held constant, what is true of average kinetic energy? If temperature is held constant, average kinetic energy stays the same. Remember, when we're dealing with gases, we're looking at the Kelvin temperature scale because that's the absolute temperature. We don't have negatives. These last two look at deviations from the ideal gas law, which we will look at on a slide on its own. But the most important thing here, temperature measures average kinetic energy. The next part of 3.5 looks at the Maxwell-Boltzmann distribution. So the Maxwell-Boltzmann distribution are these graphs, these curves that show the distribution of speed of gas molecules, whether it's different gases or whether it's gases at different temperatures. We see both. There is at least one of these questions in the practice multiple choice that you picked up. So this shows an example of nitrogen versus oxygen. Nitrogen is a lighter gas, and so more of the nitrogen molecules travel at a faster speed. The x-axis is speed. So the further out the curve goes, the faster the molecules travel. The area under the curve represents the relative number of molecules. Down here, we show gases at different temperatures. The higher the temperature, the faster they move. So the solid line here represents a higher temperature because more molecules are traveling at a higher speed. We can also see that here with nitrogen. So notice how at 1,000 Kelvin, this curve gets more flattened out because we have more molecules traveling at faster speeds due to the higher temperature. Now it's still a curve. because we still have some molecules traveling really slow. We have some traveling faster than the average. But the peak, that shows our average speed. The Maxwell-Boltzmann distribution is a graphical representation of the speed of molecules. It could be different gases, which means we look at molar mass. It could be different temperatures. Now, for 3.6, I want you to star, circle, highlight something next to topic 6. We are seeing more and more questions, both multiple choice and free response, that asks about deviations from the ideal gas law. This slide I actually just pulled from when we actually talked about gases and when we looked at real versus ideal behavior. When we talk about ideal gases are the perfect gases. They follow the kinetic molecular theory perfectly. Gases don't actually behave like ideal gases. And so we need to know the conditions when gases behave ideally, and we can use PV equals nRT for calculations, or when they're behaving more like real gases. So there are two things that happens to gases that goes against the kinetic molecular theory. One of them is if gases actually have attraction to each other. When gases have attraction, there are less collisions. So when gases are actually attracted to each other, they kind of travel in pairs or in trios. So instead of every gas molecule colliding, now you have less collisions. Less collisions means that pressure is lower than what we expect. If you see a question that says, why was pressure lower than expected? That means you're dealing with a deviation from ideal behavior. If pressure is lower, that's due to attractions. When gas molecules or particles travel at high temperatures, they are moving so quickly that they can't stay attracted to each other. They're moving so quickly that they're bouncing off of each other and they're behaving ideally. So at high temperatures, we would have ideal gases. At lower temperatures, they're moving more slowly and they're actually staying attracted to each other as they move around in the container. So at low temperatures, gas is real or non-ideal. Now the second factor that affects real versus ideal gas is particle volume. We are talking about particle volume, not container volume. So when the particles actually have a volume, they're larger than we expect. Our number of collisions actually increase because now the particles are bigger, so they're colliding with the walls of the container and they're colliding with each other more. Actual pressure ends up being higher than what is expected. So if pressure is lower, that's due to attraction. If pressure is higher than what is expected, that's because of particle volume. At low pressures, that actually means that the container's volume is larger. So at low pressures, when the container volume is larger, the space between the molecules is greater, and so the gas will behave ideally. At low pressures, when the container volume is large, there's lots of space between the gas molecules, and so the gas will behave as an ideal gas. However, at high pressures, so if we shrink the container volume down, well, now the particle volume is significant. We have to take that into account, and the gas is non-ideal. So we have ideal gases at high temps and low pressures. We have non-ideal or real gases at low temperatures and high pressures. You need to know those conditions. That means that you memorize those conditions, go for it. But it's based on attraction and it's based on particle volume. So those are the two things that affect ideal behavior. So then we switch in Unit 3 to solutions. 3.7 just talks about what a solution is and molarity. Remember, molarity is moles over liters. On your equation sheet, it says molarity equals moles of solute per liter of solution. When we're dealing with molarity, this is an example of a question that they use for solutions. Notice how they give us kind of a magnified view of what's in the container, and they give us the container's volume. When you deal with particle diagrams, no matter what the topic is, when you're dealing with particle diagrams, count the particles. So for example, here I have 4 moles in 25 milliliters. So 4 moles divided by 0.025 liters. Here I have 2 moles in 0.025 liters. I have 4 moles in 0.05 liters, 4 moles in 0.05 liters. So these two substances have the same concentration. B has a lot more substance in the solution compared to the other ones. Notice how they are different volumes though. So if you're comparing all of them, what I would do is I would just multiply this by 2, multiply this by 2, multiply this by 2, and this by 2. That way you can compare the volume, equal volumes. So that's looking at molarity. Remember, it's moles per liter. You'll see in the unit guide, it tells you they are not testing on molality. So remember we talked about molality, which was moles per kilogram. They only focus on molarity on the AP test. So molarity is moles per liter. When it comes to representing solutions, we've looked at this diagram quite a few times. Remember, a solution has a solute and a solvent. Solute is what gets dissolved. Solvent is what does the dissolving. Water is a universal solvent. When it comes to representing solutions and what happens within the solution, this shows an example and it gives you kind of a step-by-step for drawing what's happening. So here we're putting a sodium chloride crystal into water. Sodium chloride is ionic. Here's our ion-dipole forces that we were talking about with IMFs. When we're drawing what's happening, pay attention to size. Remember, cations are smaller than anions. Cations are smaller. Na plus is smaller than Cl minus. This is where, on one of the free response questions when we had to draw this is what lost people points. Na plus and Cl minus have charges because they are ions. Water is not ionic. It is not O2 minus and H plus. These are molecules. They're covalent compounds. The only thing that you could draw on the water is partial negative on oxygen, partial positive on hydrogen, not full charges. When you surround the ions, this is called the solvent cage. We usually draw 6 water molecules, but typically it will tell you how many to draw. Before we saw it said at least 4. But then the last thing is how everything is oriented. Because Na plus is positive, the oxygens will orient themselves toward the Na plus because oxygens are partially negative. The hydrogens will orient themselves toward the Cl minus because the hydrogens are partially positive. So there are a lot of things that we have to take into account when we're drawing everything. But remember, the reason that there is attractive forces here is because of ion-dipole forces. So this is how a solution is formed. We'll talk about the energetics of forming solutions when we talk about thermochem. But this is how we form a solution. Water will pull the ions apart. So then we go into 3.9. Topic 9 talks about how we can separate components of a mixture. So when we have a mixture of liquids, we cannot separate them by filtration. Filtration is when we separate a solid from a liquid. If we have two liquids, we can use one of two methods. We can use chromatography or we can use distillation. We did a chromatography lab in class. Chromatography takes into account intermolecular forces. So we look at the intermolecular forces that exist within the sample itself, and we compare that to the solvent. So remember, we have the mobile phase, which is the solvent as it moves up the piece of paper. And then we have the chromatography paper, which is the stationary phase. As the mobile phase moves up, so as the solvent moves up the paper, it picks up the samples. So in this case, if it's water, it moves up the paper, it picks up the samples, and the samples will move a certain distance based on one of two things: the size of the particles and the intermolecular forces, so the polarity. The larger particles will move more slowly. So if we notice that the orange dot only moves a little bit, well, it could be a larger particle. And then particles with a polarity that matches the solvent move farther. An easy way for us to remember it is like dissolves like. Now, we can't use that as our explanation, but that's an easy way for us to think about it. So if this is water, that's polar. If the green dot is also polar, they're attracted to each other and they will travel up the paper further. So if a sample travels up the paper with the solvent more, that means that that sample has similar intermolecular forces to the solvent. So with chromatography, here were the paper chromatography strips that we looked at in class when you guys had individual strips and you were separating dyes. The one thing about paper chromatography is we can't collect any of these samples. I can't just pull the liquid off of the paper. If you want to separate components of liquids based on intermolecular forces, based on their attractive forces, you can use column chromatography. So a second type of chromatography is called column chromatography. And an advantage of column chromatography is we can collect the samples individually. So you'll notice here we have a mixture. Over time, it goes through all of the different substances within the column, and we can actually collect each sample individually, and then we could do more analysis with that. So if we want to separate components of a liquid, we want to be able to collect the liquid, one way is column chromatography. Paper chromatography is just an easy way for us to identify something in an unknown. The second way to separate substances is distillation. Distillation separates two liquids based on boiling point. So we have to make sure that the two liquids have different boiling points. So an example is water and ethanol. Well, water and ethanol have two different boiling points. And so what we can actually do is we could boil off the ethanol first. It travels up into the neck of the flask. And because it can't escape out of the top, it goes down this condensation tube, recondenses into liquid, and then we would have ethanol over here. So we're purifying ethanol. But it's how we can collect ethanol. We're separating based on boiling points. And so ethanol and water, both hydrogen bond, but water has stronger intermolecular forces, so it has a higher boiling point. So ethanol will boil off first. So that's how we can separate based on boiling point. So the last part of solubility of solutions is looking at Coulomb's law and solubility. So the biggest thing with topic 10 is this bolded statement here. Substances with similar intermolecular interactions will be miscible or soluble in one another. This is where that like dissolves like term comes from. We cannot use like dissolves like as our explanation. Our explanation is both of these samples when they are combined in the same container, the molecules will form hydrogen bonds with each other. They form similar types. Yeah, so when two samples get added together, these two samples will actually form hydrogen bonds with each other. So this H would hydrogen bond, right, would attract to this O. This H could attract to this O. And so since they form similar types of intermolecular forces, we're able to mix them together. That's why nonpolar and nonpolar will mix. Now with ionic, we can think a little bit about lattice energy. So I have it right here. We're going to talk much more about lattice energy when we get into thermochem. But when it comes to separating an ionic substance, we can think about Coulomb's law. The higher the charges, the stronger the attraction and the harder it is to pull those substances apart. So if we're thinking about the strength of ionic substances, the higher the charges, Mg2 plus and O2 minus, have a stronger attraction than Na plus and Cl minus. We'll revisit lattice energy in thermochem, but that's looking at solutions as well. The last part of Unit 3 deals with spectroscopy. So spectroscopy looks at absorption or emission of photons. So we actually looked at spectroscopy. We just didn't know that this was the actual name. We looked at flame tests. So when we did flame tests, or we have these gas discharge tubes, this is just a gas that we're running electricity through. As we run electricity through a substance, electrons jump and they fall. That gives off light. Well, the difference between all of these different types of spectroscopy, we can actually look at how that relates to molecular motion. So College Board wants you to know these 3 types of spectroscopy and what we can figure out from those 3 types. So what that probably means is you just need to memorize these 3 types of radiation. One of them we'll be able to have a way to remember. So the first is microwave. Microwave radiation is associated with molecular rotation, so bond rotation. Here's how we can remember microwave radiation. Think about like a microwave in your kitchen. All right, inside the microwave is a glass plate. Well, when you turn the microwave on, you put something in the microwave, what happens as it heats up? Right, it spins, it rotates. So in the microwave, the substance rotates. Microwave radiation is looking at how molecules rotate. So microwave radiation is associated with molecular rotation. Infrared radiation. So we have something called IR spectroscopy that we look at with organic a lot more. IR looks at different types of bonds by looking at molecular vibrations. So single bonds vibrate differently than double bonds, which vibrate differently than triple bonds. And what we can actually do is we can look at the molecular vibration using infrared to figure out what type of bond exists. And then finally is UV vis or X-ray. So UV is ultraviolet, vis is visible. Well, UV vis is actually dealing with flame tests, gas discharge tubes. Right, visible is what we can see. Beer's law, what we're going to look at with topic 13, that's visible as well. We've looked at different types of X-ray radiation. Photoelectron spectroscopy has its own topic. That looks at removing electrons. We're looking at removing electrons from an atom. So UV vis or X-ray radiation looks at electron transitions, looks at electron levels. And so this actually ties into the electromagnetic spectrum. But the 3 types of radiations that we need to know are microwave, infrared, and UV vis. And that's given on topic 11 on the unit guide. And so kind of tying into flame tests and visible light, topic 12 looks at the photoelectric effect. So this is looking at the electromagnetic spectrum. This was chapter 6 for us. This tied into electron configurations. So we did this when we did electron configurations. With the photoelectric effect, we're looking at what happens when a photon is absorbed or emitted. So when you have energy that is absorbed or emitted, you have electrons jumping and falling back down, gives off a certain amount of energy. Well, the amount of energy that it gives off is from the electromagnetic spectrum. We can calculate wavelength. We can calculate frequency using the speed of light. This is on the equation sheet. We can calculate energy or frequency using Planck's constant. C is the speed of light. That is on the equation sheet. H is Planck's constant. That is on the equation sheet. The biggest thing with these two formulas is paying attention to units. Energy is joules. Frequency is hertz, which is per second. Speed of light is in meters per second. A lot of times wavelength is in nanometers. So you just have to pay attention to your units as you're working through calculations with the photoelectric effect. Now looking at the electromagnetic spectrum, remember the higher the energy, right? The higher the energy, the higher the frequency. The higher the frequency, the lower the wavelength. So it shows here your wavelength, and then it shows your relationships. So as energy increases, so does frequency. Those are directly proportional because they're across the equal sign from each other. Wavelength and frequency are inversely proportional because they're on the same side of the equal sign. So that's using spectroscopy and then tying in calculations. So speed of light, energy, and frequency. And then the last topic in unit topic 13 is the Beer-Lambert law. This is Beer's law. This is a lab. We did this virtual lab around Christmas. But this was a simulation where everybody had a different solution. And in the simulation, you shined a light toward the solution. It absorbed a certain amount of light. And then we were able to measure the absorbance. And from the absorbance, we calculated concentration. So Beer's law is used to measure the concentration of colored solutions. Please, somewhere on topic 13, write down that the solution has to have color. If the solution doesn't have color, it will not absorb light. So the solution has to have color. NaCl solution will not work because it's clear. Copper sulfate is blue. That works. All right, certain lead solutions might have a yellow color. Iron solutions might have an orange color. So it has to have color. What Beer's law does is it relates absorption to 3 different variables. Typically, molar absorptivity and path length. These 2 remain constant. So what this allows us to do is look at absorbance versus concentration. Most questions that we see with Beer's law have a graph like this. Absorbance on the y-axis, concentration on the x. We've seen questions that will say, if the absorbance is x, what is the concentration? And it is reading a graph. So if we have the standard curve like this, and they give us an absorbance, you follow it over to the line, you go down and you read the concentration. Because this deals with light, we look at different wavelengths. So we have a certain wavelength of light that we can shine through. If we change the wavelength, we change our results. So we will look at questions that have Beer's law tied in, look at some multiple choice answer for your response that look at Beer's law. But what this does is it looks at absorbance versus concentration.